In this video we define the basic variational problem and we are going to give the solution of the problem, but we don't prove it in this video. For the proof, see the next one. But what is the basic variational problem? How to define the basic variational problem? For simplicity, I put a graph here with two states, x1 of t and x2 of t. So in this graph we can draw the trajectory of x of t, the trajectory of the states. The 2 points, the beginning and the end points, are fixed. It means that the time t1 and t2 are fixed, and the value of x at t1 and the value of x at t2 are also fixed. So the time is fixed and the states are fixed at the beginning and at the end. And we have to find the optimal function. It is denoted by x of star t, for which the functional denoted by j has optimum, and in optimal control this optimum is minimum. And j is equal to integral of from t1 to t2 of the function v with the three arguments x, x dot and t dt. For the presented graph, for the presented trajectory of x star of t, for this x star, this j has a minimum value. So for any other x, this j is not minimum, so this is not optimum. This is the only one trajectory for which the defined functional or the defined cost function is minimal. What is the solution of this problem? How to find this x star? The solution is the following. The necessary condition for x star of t, which minimize the functional j, can be got by the solution of the so-called Euler-Lagrange equation. So this is a new concept, the Euler-Lagrange equation, and this is the necessary condition for the optimum. Here is the Euler-Lagrange equation. In the Euler-Lagrange equation, first we have to take the derivative of the function v by x dot, and we have to take the time derivative of dv over dx dot, and finally we have to take the derivative of v by x. And by these derivatives we can set up the Euler-Lagrange equation, and if we solve it, we are going to get x of t. This is x star of t, and this is the optimum of this functional. But we need a sufficient condition for the minimum and a sufficient condition for the maximum, which can be defined as I mentioned here. And of course, we need the sufficient condition for the minimum, and in this case we have to take the second derivative of v by x dot, and we have to put x star into this expression, and it must be positive. So this is the sufficient condition for the minimum. Anyway, the sufficient conditions are called the Legendre conditions. So first we have to set up the Euler-Lagrange equation, we have to solve it, and we have to use the Legendre condition.